Here is the example of surface level of detail. The previous one was source level of detail, and this is surface level of detail. Let's open it. Now we have just one source, and let's make a little simulation. That's okay. Let's build the surface. And let's see it in wireframe and more closer. In this example, surface level of detail is 10, and when I make it 5, I will see less triangles on the surface, and 2 means 2 less, and 7 or maybe 20. As I increase the surface level of detail, I will see more triangles on the surface and a more smooth surface. But after changing this parameter, you can see now I have a more smooth liquid surface. But I am using much more triangles on the surface. So now let's continue with drop size. We can continue with drop size on this example. Drop size is the size of the particles when they are alone. This means drop size is 1 here. As you can see, they are not blending with the other particles. I'm increasing the drop size to 2, and some of them are start blending with the others. And drop size is 3. Yes, many of them are blending with the others. And drop size is 4, like this. This parameter is independent from melting threshold. I will explain it later. Let me set drop size 1 and flush the surface memory and recalculate the surface. As you can see, for recalculating the surface, you do not have to flush the particle cache. Just flush the surface cache and rebuild it. Okay, let's stop this. And here is our simulation. Now I will show you melting threshold, but before starting this I will give source level of detail of 4. Let's flush the memory. Maybe 3. Yes, and calculate the simulation. Yes, now we don't have much particles on screen. Use drop size 4 and melting threshold is 4. We have this result, and melting threshold is 1. We have this result. Melting threshold controls how far particles blend together, and drop size controls the size of the particles. For example, 5. And this is drop size 1. Particles are getting smaller. And this is drop size 5. Particles are getting larger. And melting threshold 1 and melting threshold 5. And drop size 1. Melting threshold just controls how far particles blend together. Drop size controls the radius of the sphere around the particles. Yes, for melting threshold 4 and drop size 4 we get this result. To say it in another way, drop size or the radius of spheres around particles also affects the way particles blend, because in larger diameters particle surfaces will get closer to each other, like this. As I increase the drop size 1 to 2, the distance between particles get smaller. I mean the distance between the outer surface of the particles gets smaller. Particles stays same. The distance between the outer surface getting smaller. And melting threshold measures the distance between the outer surface of these spheres. If this distance is close enough, it will blend the spheres like this. I mean, it will build a surface between them. So let's talk about shrink wrap. Shrink wrap parameter is a post-process filter. In higher values, the polygonal surface of the polygonal surface that represents a liquid surface is shrinked to adjust better to particle cloud, like this one. It cannot take a higher value more than 1. This is the maximum effect of shrink wrap. If I change it to 0, now shrink wrap effect is 0, so we don't have any effect here. Now I can, yes, I will change melting threshold to 1 also. These are the actual drop sizes of particles. can control them now. Because melting threshold is 1, they are not blending each other also. And if I make shrink wrap 1, and of course drop size to 4 and melting threshold to 4 and drop size to 4, yes, now I can see a maximum effect of shrink wrap. So let's continue with the others. Now I want to start per object attributes. These parameters control the interaction between the object surface and Glu3D particles. I want to start with surface friction. I can reach these parameters easily by selecting Glu3D Object Manager button. By using the Glu3D Object Manager, we can control the Glu3D per object parameters in an ordered way. Glu3D Object Manager is a list of objects in the scene which are colliding with Glu3D particles. We can change their surface attributes, and we can also add new objects to the list, and this means the new added objects are colliding with the particles. We have two planes here, floor Glu3D and floor Glu3D1. Floor Glu3D has a friction parameter of 5 and the other is 0. So let's calculate and see the difference. Friction is an animatable parameter. This controls the friction between the object surface and Glu3D particles. When Glu3D particles touch the surface of the object, they lose their energy, and higher values result slower particles after touching the object surface. So let's stop it and build the surface. Yes, and now we can see the result. Here on the right side, friction is 5, on the left friction is 0, and we can see on the right fluid moves very slowly, but on the left it is fast. Yes, and now I can talk about the next one. Yes, now we have two spheres instead of planes. On the left side, adherence is 1. This is the maximum. And on the right side, adherence is 0, and this is the minimum. So let's calculate and see. Adherence controls the particle. yes, here we can see on the left side, when particles touch the surface of the sphere, they act as they are glued on the surface, because parameter is 0, and we can reach this parameter by clicking on this button, and they are here. Right side bounce is 100, that is the maximum value. And let's calculate the simulation. Bounce controls how much particles bounce after touching the surface of an object. We can also animate this parameter. While filling a container, it is better to minimize this parameter to 0 to avoid unnecessary particle flickering while particles touching the surface of the container. And after liquid is settled, if we plan to animate the container, we must increase this parameter to avoid particles going out of the container, I mean passing through the faces. And so let's stop this, build the surface, and let's see what happens. That's enough, I think. Let's see it in front view. Yes, on the left, bounce is 0. We can see particles are not bouncing after touching the surface, but on the right, bounce is 100. That was the maximum, and particles are bouncing after touching the surface. And my last example is about collision gap. Collision gap controls how far particles collide with object walls. We cannot set this distance to absolute 0. It is impossible. And if we reduce this value too much, some high-speed particles can pass through the surface they touch. And let's see in front view. So this is the collision gap. This distance is the collision gap, and on the left side this was 0, but on the right side this is the collision gap. On the right side it is set to 0.15. As we can see, we cannot reduce this distance to absolute 0. We always have a little distance between the particles and the surface.